slide. We'll open there. Now, let me hit these few announcements before we go any further. This class of 12 strong students, I think it's down to 11 because we added one and dropped two, and two never showed, never paid, I'll say. One never showed and one never paid. So we're down to, I guess, 11 strong students now. And of those 11, 3 have turned in papers. 3, okay? Please, folks, don't forget about your papers. I think you only have 1 or 2 weekends left. I meant to check and I haven't. One class told me Monday was the last day of class, not this coming Monday, the following one. And another class said, no, it's the previous Wednesday. I thought, so I haven't checked to see. I thought we were supposed to have class that Monday, is that the 31st? Is that the last day of class, or is that the beginning of finals?
Because I had another teacher tell me that we don't end until the first week of August.
Well, I know finals were the first week in August, but that's July 31st, I think. So is that the last day of class or first day of finals? Okay. Well, we'll find out. If it's the... What's that? You can, but whatever I get and opens up, that's what I grade. I've had some things come in that are really weird formats. I don't know if that's how it left the student or if the email screwed it up. So I'll take it, but I grade what I get. So I think most of the time it's probably the student really didn't proof it very well because we're in a hurry and didn't notice that the format was really, really screwy. But it could have been the email messed it up. I don't know. But anyway, I've only got 3 out of 11 papers. Please don't forget your paper. Get that done. While I'm mentioning that, I've got 1, 2, 3, 4, 5, 6, 7, 8. Well, let's see. 1, 2, 3 people haven't turned in the first test. That's why I can't return your first test to you, because 3 people haven't turned that in. And then the second test, y'all have had for a little bit now, and I don't have any of those in yet. Please be working on those too. I warned you at the first of the term, don't put the papers off till the end because everything gets all bunched up and crowded then. So please try to get things taken care of sooner rather than later. All right, other topic. Next, I think it's Tuesday. I've got to check on this date too. We have what they call a planning hearing. And the math planning hearing is at 10 o'clock in the morning on the Birmingham campus. That's going to screw up my differential equations class, but we'll be able to manage that. I don't know if I'll have time to come out here and teach for an hour and then go over there, or if I just need to cancel the whole class. It just, it depends on what I can get done tomorrow and this weekend. If I can get everything pretty much done, then I'll be okay. But it will mess with my office hours, because normally on Tuesday, Thursday, office hours are 10 till 12, and because that's going to be 10 till 11, and I need to be there for the first part of the next hearing, natural sciences, because we do some things jointly. I plan to leave there by 11:30, okay, which puts me back here right at 12, which is right when my class starts in the afternoon. So basically my whole bunch of office hours, 10 to 12, are wiped out next Tuesday. I think. I'll check on the date of that. However, the afternoon office hours from 3:30 until 5:15, they should be okay. And after that, I think all things should be fine. Okay. I think that's all. Any questions on anything we've done so far? Okay. If not, we were in Chapter 4, Applications of the Derivative, 4.2, Extreme Values, and we were just looking at, or just had pulled up this slide. Didn't have a chance to do anything with it. I don't recall that we did anyway. But this is, the question is, how do we find the local extrema? Okay? In other words, the local minimum, local maximum. Okay? Now, the word local is important. The absolute maximum, say, of this function here would be this point up here. That's as high as it goes. Well, that's at the end value. Okay? That's not a local extreme, that's an absolute extreme. The local extrema are those that within their neighborhood, they're either the minimum or maximum or minimum points. This one doesn't have a neighborhood on this left-hand side. It's not a local extrema. This is not a local extrema, even though it's the highest point near it, but it doesn't have a neighborhood around it. You've got to have a neighborhood all around the point. So those have got to be interior points. Well, on this graph, what would indicate where those local extrema are? You can look at the graph and say, there it is, there it is, there it is, yeah. But that doesn't tell you much. How can you find out analytically? What's true about every one of those points? The red lines are a hint. The caption is a hint. What is horizontal? Tangent line. And how do we find the tangent line? One of those questions. Take the first derivative, exactly, and that will give it to you. So if you know the function, they give you the function, take the derivative of the first derivative of that function, set that tangent, that first derivative equal to 0, find out what points for x, make that happen to be 0, then plug them in and you've got the y values too. So that's how you find your local extrema. Okay? For a smooth, continuous function, the tangent line is horizontal at the local extrema. However, that's not the case for this function. That is a continuous function, but it's not very smooth. So what's true about how could we find the extreme value there? And again, local extrema, not the absolute, and these wouldn't even be absolute. What? They only picture one here, but what local extrema do you see here? Any? Well, that's certainly a local extreme, right? It's the minimum value anywhere in its neighborhood, right? What they didn't do is say there's a local maximum and there's a local maximum, because in this neighborhood, that point, but these two we can find through the first derivative. What about the first derivative of that? Okay, read the caption. This occurs at a point where the function is not differentiable. So what do we have? It's either where the first derivative is 0 or where the first derivative does not exist. Those are the two cases that we'll investigate for a local extrema. We don't have to do the graphs. We can find them analytically using our first derivatives. Take the first derivative of the function and any values where that first derivative is 0, the x values here, that will give you your x points. Plug that into the function itself, you get the y value. That will give you your local extrema on smooth functions. If you got a function that's not smooth, then you still do first derivative. Where that exists, set it equal to 0, that will give you local extrema. But where it doesn't exist, that at least is a possibility of being another local extreme. And Tina's here. All right. We're on page 202. This is chapter 4, application of the derivative 4.2, extreme values. And we just talked about the two tests. And here we'll give those two tests. And we call those extreme values, local extrema. We call those our critical points. Okay? So here's a definition for you. A critical point, if you have a number C, and they showed that in both of the previous two figures, the number C in the domain of F is called a critical point Okay? If, and here's your two cases, either the first derivative at c is 0, or the first derivative at c does not exist. Those are your two criteria for critical points. In other words, they're candidates for where a local extreme may be. Doesn't guarantee a local extreme will be there, but those are the places where it could exist. So either where the first derivative is 0 or the first derivative does not exist, the value c. Okay? And that's called a critical point. Now, I sort of don't like that terminology. And here's why. I would say a critical value for the x. Because when you say point, to me that means ordered pair. Okay? Guess what? C is not an ordered pair. For that to be the critical point, you would do C for the x value and f of C for the y value, because that would be the y value, right? So I would call this a critical value. C, a number C in the domain of f is called a critical value if either f prime of C is equal to 0 or f prime of C doesn't exist. If you wanted to call it a critical point, then a number C in the domain of f whose y value is f of C, C comma f of C would be the critical point. That's just my being a little picky about it, but I really think they're being a little sloppy on their nomenclature here. All right, this I think represents example 1. So let's see if we can get this done. Find the critical points of, here's the function, okay? Let me get my pen darkened. Here's the function. F of x is equal to x cubed minus 9x plus x squared minus, plus 24x minus 10. It says find the critical points. Okay? I would say without drawing a graph, okay? They've drawn a graph for you, fine. How would you find the critical points? First step, take a derivative, okay? So f prime of x would be what? 3x squared minus 18x plus 24. Okay? What are you going to do with that derivative? Set it equal to 0, exactly, because your critical points are going to be where the first derivative is either 0 or doesn't exist. Now, time out. What kind of function is this? This one. You're right, that's a quadratic. This is a linear. Say again? Linear. No, it's got cubes and squares. Linear, the maximum exponent can only be 1. But it's more general. It's a polynomial function. Polynomial functions are smooth and continuous everywhere. So you're not going to have any places where the first derivative doesn't exist, because polynomial functions are smooth and continuous everywhere. Okay? So you don't have to worry about the not exist. If you've got the first derivative, it's going to be pretty obvious if there's a point where it doesn't exist. That means you're either going to have a variable in the denominator, and if that variable could make that denominator 0, doesn't exist there. Secondly, if that variable was in a square root or any kind of even power root, okay, anywhere that integrand would be negative, can't happen, okay? And if that variable was in a log function, logs can neither be negative nor 0, okay? So those are the things you look for. This is a polynomial, smooth, continuous everywhere. So the only thing we're going to be interested in is where they're equal to 0. So we set it equal to 0. What do we do then? What's the F word? All right, factor. What would be the first thing you would tend to factor out here? 3. I like it. Factor out a 3, and what do you have left?
3 times
X squared minus 6x. And here's Lauren. If I can find you, there you are. Right there. All right. Okay. X squared minus 6x. Any more? Plus 8. And set that equal to 0. Okay? Now, factoring the 3 is important. When you're trying to find the values for x and make that equal to 0, who cares about the 3? You can divide it out. So we don't care about it. Are you through factoring? No. We can factor a little bit further. And what does that give you? X minus 4 times x minus 2. Set that equal to 0. And again, I said the 3, for the purposes of finding the critical point, has no impact here. 3 can never equal 0, right? So forget about the 3. That could equal 0. What would make that equal 0? Set, right, x equal 4 or x equal 2. Now, they would call these the critical points. I call them the critical values for x. Okay? Just for funsies, though they don't do it in the text, let's find out what the value is for that function when x is equal to 4 and x equal to 2. Okay? So let's do our original function, not the derivative. We know there's going to be 0 there. Let's do f of 4. What would that be? Three times. No, it's cubed. Oh, I'm sorry, it's not 3 either. Goodness gracious, what's wrong with me? I was doing exactly what I said not to do, okay? Take the function. 4 cubed is 64 minus 9 times say again? No, we're doing 4, yeah. 9 times 4 squared is 16 plus 24 times 4 minus 10. Okay, let's see what that is. 64 minus, oh boy, 9 times 6 is 54. 5 and 9 is 14. Plus, that would be 1696 minus 10. Ew, okay. Let's add the positives together and you get 160. Add the negatives together and you get a minus 154. And that's going to be 6. So that value right here is going to be 6. So obviously they didn't draw this graph to scale. Okay? Because that point will be, I would say this is the critical point, would be 4, 6. Critical value 4. And that's what the book is focusing on. They said, find the critical point, so I'm finding the critical points. Okay, let's use the 2. What is f of 2? What would that be? Again, there's the f function. 8 minus 36. 9 times 4 is 36. Plus 48 minus 10. Again, add the positives together, and you get 56 minus 46 would equal 10. So this value up here would be 10. And that looks about right. My markings probably aren't quite to scale, but pretty close. So the second critical point, the critical value 2, the critical point would be 2, 10. All right, good deal. They didn't ask for that. They just said C equal 2 and 4. Those aren't points. Those are values, okay? Now, that was example 1. Any questions on that? Oh, I'm sorry, I should have said it. We're on page 202, chapter 4, applications of the derivative, section 4.2, extreme values. Okay? I was making the point before, the absolute maximum then would have to include the endpoints. If this had an endpoint, this didn't indicate it did. The local extrema, maximum and min, they have to have values on either side of it. And see this, the way they've drawn this, this would be your absolute minimum, but it's not a local minimum because you can't draw a circle around it and include all points on both sides. In fact, if you did that, you'd see this keeps going down. So it wouldn't be a minimum at all. This looks to be an absolute maximum the way they've drawn it, but you can't get any values over there. If you could, it would keep on going up. So yeah, that's, so we only include the interior points, the points that have values on either side of them. Okay? So, those are the local extrema. That's the critical points, or critical values. All right, let's look at example 2. Any other questions on this? Okay. Here is a very famous function. Find the critical points of f of x equal absolute value of x. Okay, there's the function. Okay, what are we going to do? What are we going to do? What do we do with that? What do we do with the drunken sailor? No, that's no. This, if you haven't noticed or run into it before, this is a, sure, we know what that means, absolute value. But to write it analytically, or analyze it analytically, this is a piecewise defined function. It has one value over here, another value over there. We put them together and call it absolute value, but the real way, or the most instructive way to write this is writing this as f of x is equal to x when x is, when is f of x equal x? F of x equal x would be this graph right here, right? That's the identity function. Okay? When is that true? You see, this is true everywhere over here. But when is that true for the function? When x is greater than or equal to 0. This is x when x is greater than or equal to 0. And what's the other value? Back over here. What function is that? Minus x. Anytime x is less than 0. Isn't that what absolute value is? If the value x is positive, then it's just a value, right? But if the value of x is negative, the absolute value of it is the opposite of it. In other words, the negative of x, right? So this is the way to write for analytical purposes what your absolute value is. That's what absolute value means always, okay? So this I can't take a derivative for. This I can. Let's take the derivative f prime of that. What's the derivative of x? 1. And that 1 is anytime x is, I'm just going to leave it as greater than 0. Okay? There's going to be a reason for that. And let's take the derivative of the second part of that function. And what would that be? Negative 1. And that's anytime x is less than 0. So guess what, folks? What is the derivative at 0? It's negative 1 coming from the left, positive 1 coming from the right. That derivative doesn't exist at 0. If you were to plot that or graph the derivative of this, here would be your derivative there. Here would be the derivative there. What is it at 0? Has no value. Ding, 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 ding. That is your critical point. It's where your first derivative is 0, or the first root of it doesn't exist. First root of it doesn't exist at 0. It exists everywhere positive, everywhere negative. Doesn't exist at 0, so therefore your critical value would be x equals 0. What's the critical point then? Plug 0 in here, and what do you get? What's the absolute value of 0? 0. So the critical point would be 0, 0. I'm just making a sort of a special distinction there. I really think that should be called the critical value. The book calls it your critical point. That is your critical point. That's the critical value. X equals 0. Okay? So, two conditions for an extreme value, where your first derivative is 0, or first derivative does not exist. Now, I'm sorry, said that a little too generally. Those are your critical points. You're not guaranteed that the critical point is going to produce an extreme value. In these cases we've just done, yes, it does. We will see circumstances where your critical point may not be an extreme value. And we'll see those. Before we do, I think, let's look at Fermat's theorem on local extrema. Now, we were talking earlier, before some of you came in, on the critical need for you to get your papers done, right? We were on critical stuff, and some of you have already done your papers, but those who haven't, you have either 1 or 2 weekends left. I mean, this coming weekend, maybe your last weekend, I just don't know if the last day of class is the 31st or if that's the first day of finals. Does anyone recall? Say again? August 1st is what? August 1st is not the last day of finals. It may be the last day of class, but it's, oh, class. Okay. Last day of finals is then sometime later. So if Tuesday the 1st is the last day of class, then you have 2 weekends. If Monday the 31st is the last day of class, you still have 2 weekends. But if next Wednesday is your last day of class, it means you only have 1 weekend left. So check. You can go to the Boston State website. On the main page, the home page of the website, across the top of the page, there's tabs. One about 4 or 5 down says, maybe a little further, says academic calendar. Click on that and go for the month of July, and then go to the month of August. See when they say the last day of class is. Last day of class, if it's it does say July 31st. That's a Monday. So that gives you 2 weekends, because we will meet and have class on Monday morning. Then I'll give you your final exam. You can turn it in. And when are finals due? By Thursday or Friday? That means finals would be I think it's 1st through the 3rd. Is that right? Okay. So Tuesday, Wednesday, or Thursday. You can return your final to me any day, Tuesday, Wednesday, or Thursday. So I will give you your final exam on Monday the 31st. So that gives you 2 weekends for your paper. Okay. Don't put it off till the last weekend, folks. Get moving on it now. Okay. All right. So here's theorem 2. Fermat's theorem on local extrema. If f of c is a local minimum or a local maximum, okay, f of c is a local minimum or a local maximum, then c is a critical point of f of x. Very well said. If f of c is either the minimum value in a local neighborhood of c, or if it's the maximum value in a local neighborhood of c, then c is a critical value. okay, of f of x. They say a critical point. If it's a critical point, it should be C f of C, okay? That'll be your picture there. Okay, so that's Fermat's theorem on extreme value. Notice what it doesn't say. It doesn't say if C is a critical point, then f of C has to be a local minimum or maximum. It may be. Quite often it is, but it doesn't have to be. This conditionally quick statement only goes one way. If that's true, this is true. That doesn't imply, if it implied both, they say if this, now if and only if this was true, this would be true. That would mean it goes both ways. If it's just an if there, that means it only goes one way. If that's true, this is true. Not guaranteed that this being true is going to be that, because it won't always. Most of the time it will, but not always. Okay? I'm getting ahead of myself here. They do a little thing on proving this. We really don't have time to do it, so let's just show the graph. Well, they don't even show the graph of it. Here is the first thing they do in that proof is that definition of a derivative, right? When you're starting to take a limit, okay? If this thing was greater than or equal to 0, for any h greater than 0, that means this is a little bit greater than that, as long as h is positive, okay? Then this numerator would have to be positive. This would have to be a little bit greater than that. So that couldn't be a critical value, okay? Next thing they note is if this thing right here, f of c plus h, which is the first part of your limit, minus f of c over h is less than or equal to 0. If this is less than or equal to 0, if h is less than 0, okay? Not sure they quite said that right, but anyway, if h is negative, then this has to be positive for that to be true. Positive or 0, okay? So both of those gave you that. I'm not sure that's what they really intended, but that's what they have. So that would then produce this. I meant to blow up the other one. I forgot to. Boom, I blew this one up. Okay? So if you're greater than, if this thing right here, yeah, they did make that. If f of c plus h minus f of c is positive, for h positive, that means you have a positive slope. Okay? If f of c plus h minus f of c over h is negative, meaning that h has to be negative, this to be this, then this would be a negative slope. Okay? The only place where it could be 0 would then be at that point down there. Okay? Now, remember those before you take the limit, those were secant lines. Secant line between this value and that value, secant line between this value and that value. Okay? Negative here, positive there. So as you let the h approach 0, that comes in closer and closer, and then finally the only place it could be. So if that is and remember the given here, that's a minimum or maximum. They showed it as a minimum. Everywhere else, the first derivative is not 0. It is 0 there. Okay? That's what they're getting toward. Okay, now, theorem 3, which kind of builds on Fermat's theorem, theorem 2, extreme values on a closed interval. Okay? Assume that f of x is continuous on a to b. Now, if f of x isn't continuous, you really can't talk about maximum min, can you? Because if it ends here and picks up there, what are you going to call a maximum minimum? So, not going to do it. So we're going to assume that f of x is continuous. May not be derivative, differentiable, but it is continuous. Okay? Assume that f of x is continuous on this closed interval a to b. Let f of c be the minimum or maximum value on a to b. Okay? Now when they say it that way, that includes the endpoints. Okay? If it's a closed interval, then a and b could be, then c is either a critical point or one of the endpoints. Okay? If that is just a maximum value, not a, and remember I said the key word there was local. If they had said local minimum or maximum value, then who cares about the endpoints? It's got to be, that would then be a critical point. Okay? But if it doesn't say local and says maximum minimum value, then C is either a critical point or one of the endpoints. Goes back to what we were doing before. And frankly, I don't see why they make such a big deal about it, but they do. Okay? So that's theorem 3. Oh, and by the way, let's see. Yeah, this should have been the preview. Should have been before that last slide because it is in the book. What I was saying before, that Fermat's theorem only goes one way, it's not a two-way theorem, is this. Fermat's theorem said if f of c is a max or a min, well, why decided to show us that that's so nice. Yeah. Okay. Glad you're here. You were looking for me yesterday?
Yes, sir.
Okay.
I put up a form.
What's that?
I have to go get another form to change my schedule. I mean, my major.
Oh, I see. Are you a Lawson student or are you a transient?
I'm a law student.
Oh, you are? Okay, I didn't know that. I was thinking most of you were transient students. I knew a couple of you were Lawson. You're transient, aren't you? Yeah. You're transient, aren't you? Yes. Yes. Ricky, you're a Lawson student, aren't you? No, you're transient too? Okay. So you're the only Lawson student I got so far. I think maybe, well, let me see. No, Tia's transient. Angela, I'm not sure about Angela. Shakina is a Lawson student. Jasmine's a Lawson student. Will's transient. Mostly transient. Okay. Good deal. Okay, remember Fermat's theorem? I said it only went one way. If C was a local minimum or local maximum, then C is a critical point. Okay? It doesn't go the other way. Okay? Because here, what you reckon the first root is right there? 0. So that makes 0 a critical point. Is that a local maximum or a local minimum? No, it's neither. So this has another name. We'll later call this an inflection point. And there are other values that could be inflection point, but this is an example of an inflection point. First derivative is 0, but it's neither a maximum or a minimum. Okay? So the tangent line at 0, 0 is horizontal. The f of 0 is neither a local minimum or a local maximum. So therefore, Fermat's theorem is only a one-way theorem. If f of c is a local minimum or maximum, then the c is a critical point. Absolutely. But if c is a critical point, that doesn't guarantee that f of c is a local minimum or maximum. Okay. And that's the conceptual insight, and they call it a false positive. It looks like it could be, but it may not be. And this, by the way, the function is f of x equals x cubed. What would be the first thing we would do if we're looking for a local minimum or maximum? Are there questions? Take a derivative. What would be the derivative of that? 2x squared. And then what would we do to it? Set it equal to 0. 2x squared equals 0. Where's that equal to 0? At x equals 0. So that is a critical point. Critical points are where the first root is either 0 or undefined. It is 0 there. But when you test it, you see it's not a local minimum max. Because it's increasing here, it's still increasing there. That's leading us to what we're going to do next. Okay? All right. We're going to do example 3. Here's a table that's going to result from it, but let's do example 3. Find the extreme values of f of x is equal to 2x cubed minus 15x squared plus 24x. Does this look sort of familiar, but it's not the same as the one we did before, plus 7 on the interval 0 to 6. What did I say one of the key words was? If it said local extreme values or local extrema, then we do critical points. But this says find the extrema, okay? Not local extrema, any extrema. On a closed interval. That's the other dead giveaway. Now we have to consider what beyond our critical points for our local extrema. You have to consider the critical points, but you also have to consider the endpoints. Very good. Okay? So, what do you think you're going to do first? Take a derivative. Good. Okay, f prime of x is equal to 6x squared minus 30x plus 24. Right? Done. Then what do we do with that? Second? Okay, we set it equal to 0. That's what we're looking for. Places where the first derivative is 0. Okay? And then I agree the next step is a factor. How would you first factor? Factor out of 6, leaving us, second, x squared, right? Minus 5x plus 4. Set that equal to 0. I'll give you a hint. 6 is never equal to 0. So we're not going to really worry with the 6 anymore. Okay? Not in this universe anyway. But can we factor the polynomial any further? The answer is sure we can. How does it factor? X, second, minus 4, x minus 1. Okay? And what does that tell us? Where is that equal to 0? 6 is never equal to 0. But x minus 4 may be 0. Where? X equal 4 or x equal 1. So those are our two critical values. Okay? So it said find the extrema. So what we're going to do, those will be two that we'll consider. But we've got to consider two more. And what are those? Your endpoints. Okay? So let's plug and chug, folks. Okay? Let's start with the left-handmost endpoint, f of 0. What's that equal to? F of 0 is equal to? Nope. Oh, you starting and do it in pieces?
It would be the 7.
7, okay. That's equal to 7 because first term 0, second term 0, third term 0. 7. Okay? The next one under consideration is f of 1. Okay? What would f of 1 be?
Oh, we use some I, that's that?
Yeah.
That's a 6.
Yeah, this is your f function, right? So what is f of 1? So we're considering that point, that value, that value, that value, and that value. Your two critical points, critical values, and your two end values. Okay? So what is f of 1? 2 minus 15 is negative 13, plus 24 is plus 11, plus 7 is 18. So far it looks like we may have a max, but we could also have a min there. Let's continue. The next value would be f of 4, and what would that be? I think I'll have to write this one out. 2 times, what's 4 cubed? 64 minus 15 times, what's 4 squared? 16 plus 24 times 4 plus 7. All right, that would be 128 minus, someone's going to have to help me here. 240, very good, plus 96, all right, plus 7. All right, let's add our positives together, and you get, all right, 224. Second, your final answer?
That's 128 minus 240.
Oh, okay, you're doing one at a time. Okay, negative 112, okay, plus 96 would be, or had you done it all? I don't know. I don't think you had. Do them all. If you got second, negative 9. Okay, looks like we have a new winner for the absolute minimum, or we don't know that it is, but a minimum. And then we got one more to do. Oh boy, f of 6. Okay, got to plug that in. 2 times 6 cubed. What is that? Second? 216 minus, you can do all this on the calculator, you don't have to write it out like this, minus 15 times 36 plus 24 times 6 plus 7. You got calculators, do it. Say again? 46. 36. 43. Okay, I don't hear well, sorry. 40, well, I don't erase well either. Okay, 43. All right, what's our final verdict here? Okay, let's go back and review the question. Find the extrema of this. Okay, the absolute minimum is at f equal 4, or negative 9. Absolute maximum would be at 643. Starting at the end point, if you're starting at 7, okay, then when you go to 1, you go to 18, go to 4, you go to negative 9. That means 18 is a local maximum. You know that these two have to be local extrema. So that's a local maximum. This is a local and absolute minimum. And that is a absolute maximum. Okay? This one, nothing. Okay? It's an endpoint. That's all it is. It's starting at 7, going up to 18, down to negative 9, and up to 43. Okay? So you have a local maximum at 1 118. A local and absolute minimum at 4, that would be 4, -9, and then absolute maximum 6. 643. All right, that's what they include here. They just say the extrema, which is absolute maximum, absolute minimum. But you could say, because this is a critical point, that's a local maximum, because it's greater than 7 and greater than -9. So it might be a local maximum. And here is Angela. All right. We're on, just finished example 3, bottom of page 203, chapter 4, applications of the derivative, section 4.2, extreme values. All right. Now, any questions on that before we move on? Oh, and by the way, there's the graph of that one. I wondered where the graph was. There it is. All right. And this is scaled really weird. This is 1 on the X scale. That's 20 on the Y scale. So it's really a weird scaling here. At 0, it's 7. At 1, it was, what was it? 18?
Yeah.
Okay. At 4, it was -9. And at 6, it was 47 or something like that. 43. So this is not an extreme value at all. It's not a, it can only be a local maximum or minimum. It's neither of those. This is a local maximum here. That's not what they're asking for. This is the absolute minimum here, absolute maximum up there. Okay? But this one is a local maximum. This is just an endpoint. There's none of the above. Okay? Now the book, when they say the local extrema, they mean only local max, not local. When they say extrema, they mean absolute maximum, absolute min. Those endpoints generally aren't as important as the critical points. So I like to focus more on the critical points. All right, here's our example 4. Here is the function right here. F of x is equal to 1 minus x minus 1 to the 2/3 power. Okay? It's on a closed interval, and they're asking for, find the maximum of this on that. They're not asking for the min, just the maximum value on that closed interval. Okay? Guess what we're going to do first? Take a derivative, okay? So let's do f prime. All right. Now they've written this, thank you very much, in exponential notation, which is the way to go, in my mind. Goodness gracious. My eyes are so dry. All right. What is the first derivative? Anyone want to venture a guess about the first derivative of 1? 0. All right, we got that one done. All right, let's do the next part. What would you do then? Negative 2/3. The negative from here, the 2/3 from there. X minus 1 to the negative 1/3. Okay? And then you would do a chain rule and do the derivative of the inside, but derivative of x is just 1. So you don't get anything out of doing that. Just another factor of 1. You can have many factors of 1 as you want. It doesn't change anything. Then what do we do with that derivative? Set it equal to 0. That's what we're looking for, the places where it's equal to 0. All right, now, Even though to take a derivative and later to integrate, I like to have things in exponential notation, I don't see them as clearly unless I put them in radicals. Okay? So well, I don't know if radicals are important. Yeah, let's do it. So this is going to be a minus 2 over 3, but this is a negative exponent, so that's going to be an x minus 1 to the 1/3 power. And if you then wanted to take that one more step, minus 2 over 3 times the cube root of x minus 1. Okay. Now, what are some things we have to watch for? Okay. If you set that equal to 0, do you think it will ever equal 0? No, because for a fractional form to be 0, the numerator would have to be 0. Is 2 ever 0? Never, ever. It can't be, okay? So this does not have a critical point. Oh, I'm sorry. Does not have a place where the derivative is 0. But what's the other concern for a critical point? Second? No, this is we're strictly dealing with, right now, we're strictly dealing with that derivative. What are the two conditions of a derivative that give us critical points, critical values? When it's 0, and it's never 0, and when it doesn't exist. Does that derivative ever not exist? Remember, I told you there are a few things to watch out for. We go over them again. Variables in the denominator, variables under a radical, when that radical is to an even power, are variables that are within a log argument of a log function. This has no logs, okay? And it does have a variable in the denominator. It does have a variable in a radical, but that's a odd radical. So there's no problem there, okay? But it does have a variable in the denominator. What can that never be? 0. Would any value of x make that 0? Absolutely. Second, x equal 1. So x cannot equal 1. Looking at that, we say x, how would I say that? X equal 1, the f prime, let's just write it this way, f prime of 1 does not exist. Okay, that's probably the better way of doing it. So that is a critical point. Okay? Now we do the critical point and our endpoints. Okay? Now we go back to the function, not the derivative of the function. And let's start with a negative 1. F of negative 1 would be what? Well, what do you first see? Right past the equal sign. 1, okay. Minus is the next thing you see. And then we'll plug in negative 1 minus 1 to the 2/3 power. Okay? That's going to be this endpoint. Okay? In value. Okay, so this will be 1 minus the cube root of negative 2 squared. Okay, that's what that means. So that's going to be 1 minus the cube root of 4. Okay, and I don't know what that is. It's something between 1 and 2, because the cube root of 1 would be 1, the cube root of 8 would be 2, so this is somewhere in between. So it's 1 minus a negative number greater than 1. This is going to be negative. Okay? I don't know the value. You can plug it into your calculator and see what the value is, but it's going to be a negative value. So that's your low end point. Let's go to your critical point where x is equal to 1. Okay? So f of 1 will be what? One minus, second, okay, 1 minus 1 to the 2/3 power, right? What's 1 minus 1? 0 to the 2/3 power is 0. And 1 minus 0 is 1. Okay. So let's move on to the other endpoint, which is f of 2. Okay? What would that be? 1 minus 2 minus 1 would be 1 to the 2/3 power, and that would be 0. All right. Now you see now why I didn't actually waste the time, take the time to evaluate that first endpoint. All I was really interested in was going to be negative, because f of 1 is going to be plus 1, and f of 2 is going to be, that's the second endpoint, that's going to be 0. So that makes the negative value, whatever that happens to be, x equals negative 1, the absolute minimum, and x equals 1, the absolute maximum, and that would be value 1. And f of 2 is an endpoint, okay? It's not your max, it's not your min, and you notice it's not even going to be a relative max or min, so it's just a point. So sure enough, that's the value. Do they show the table for it? I think they do. Yeah, here's the table for it. To me, the table is almost just redundant, but fine. Now, the book and I differ a little bit. It doesn't really matter how you list them, but I like to list from lesser to greater, okay? You notice I did that. Endpoint, critical point, endpoint. That way, when I look at this, it's the way, if I looked at this, I'd say this is starts high, goes negative, and goes back high again. But this would be a minimum. Well, minimum is right, but if it was more involved with it, this would give us the same thing. This is neither a max or a min, that would be the max. So sure enough, just looking at that, there's the max, there's the min. But I like to look at everything in between, and that lets me know if some other critical point may be a local max or min. The book's not concerned with that. In reality, I'm always concerned about local max and min, but the book doesn't seem to be. Okay, so there's the table. I just like to go lesser to greater. They do critical points first, endpoint last, whatever. Okay. Here's another one. This is example 5. This is a logarithmic. No, it isn't. Okay. Yeah, it is. Okay, I'm sorry. I didn't read far enough. It's a logarithmic example. F of x is equal to, I just read x squared minus 8. I didn't see the log x there, on 1 to 4. And they say find the extreme values, and when the book says that, they mean extreme, the absolute maximum, absolute minimum. Okay? But what do you have to consider? Say again? You consider several values. What values do you consider? The second? The endpoints certainly are 1, so we're going to consider x equal 1 and x equal 4. Any others? Okay, yeah, you're looking at the graph, but how did they get that analytically? What are we doing in this section? This chapter, yeah, finding derivatives, application of the derivative. Good hint, critical point. So you do endpoints and critical points. I'm going to use their terminology because it sort of matches better. So to get the critical points, we take the derivative. F of x is equal to what? Two x, a good start. 8 over x. Done. What do we do with it? Okay, we do two things to it. Okay? You first look for values that it's not defined. Any of them pop out at you? Any values that x would, that derivative would not be defined. Okay, what are the three things we consider for non-definition? Not defined? Here we go again. Variables in denominators, variables under even roots, radicals, and variables after logarithms. Now the function has a logarithm, but the derivative doesn't. So no logarithms here, no radicals here, but what do we have? X in the denominator, and what would you have to exclude here? X can't be 0. But guess what, team? 0 is on the interval. So if they had said from -1 to 4, of course they wouldn't say that. Why not? The function's not defined at -1. And why they don't include 0, the function's not defined at 0. You can't take the log of 0. So therefore, 0 is a non-starter here. But you look at it and make sure that's true. That is a place where the derivative is not defined, but it's not on your interval. So forget about it for now. So what else do we, if we've excluded where it's not defined, what's the other thing we do with the 0? Someone may have already said it. Two places where your critical values could be. Where the function isn't defined, we've already wiped that one out. What's the other? Where it's equal to 0. Now this is going to be a little more challenging, not too bad, setting that equal 0. How would you determine the values of x that would make that equal 0? Add which over? Yeah, I like that idea. I'll show you another way in a second. Add 8 over x to both sides. Okay, that's a legal move. That would give you 2x. These go to 0 is equal to 8 over x. Now what? Take it. Okay, make this 2x over 1. Do a cross multiplication. Okay, that would be, say again. That would be a proportion, and how you solve a proportion is 2x squared equal 8, right? Okay? It's sort of early in the morning, isn't it? Okay. Now what would we do? Divide out a 2. I like it. Okay, and that gives you x squared is equal to 4. And that would imply x equal plus or minus 2. Okay? Sorry. My head's clogging up again. Okay? Now, those have the potential of both being critical values, but what can we notice about one of them? X equal minus 2, again, is not in your domain. Throw it away. Ignore it. We're not interested. X cannot equal minus 2 because you can't take the log of a negative number. That one's a non-starter. But 2 is in the domain. That one we have to consider. So that just gives us the 3 to consider. So let's do f of 1. What would that be? That's your endpoint here. That would be 1 minus 8 times the, right. Does anyone happen to know, goodness, I did this yesterday too. 1 minus, what is the log of 1? 0. So that's just 1. F of 1 is equal to 1. Let's go to the next one, which would be positive 2. F of 2 would be x squared minus, sorry, I got to sneeze. Okay, I think I was holding it back a little bit now. F of 2 is equal, oh, sneeze came up and threw me off stride. Okay, you're absolutely right. I thought you were golfing and you said 4. No, never mind. Okay. That would be 4. 2 squared is 4 minus 8 log 2. Pull out the calculators, folks. Okay. Do the calculation, see what you get. I can almost guarantee you it's going to be a negative number, right? What do you get? Negative 1.5. We'll put that as approximate. I'm sure there's more digits, right? And then we get to the last endpoint. F of 4. Okay? Goodness gracious, my eyes are so dry. Okay, what would that be? 16 minus 8 log 4. Okay? Now, I don't know my log tables that well, so you do it on your calculator. 4.5? 4.9? Okay, and that's approximate. Hey, I can hardly keep my eyes open without them just drying out. Okay, so what can we conclude here? Local, not local. Your extrema, extreme values. Did you say 1? Okay. The minimum is at negative 1.5 at x equal 2, and the maximum is at the endpoint x equal 4, and that would be 4.9, I think it was. Okay, sure enough, there's your min, and there's your max. They said negative 1.55. Didn't have a calculator, so I'll take one of your words for it. I really don't care which. Okay? Okay, but you see how you do these. Okay, the next one's going to be a little more involved. Oh, here's the table that they did. Of course, they do critical points first, then endpoints. I like to call those critical values and end values, but they call them points. And again, the smallest number is a minimum. The largest is your maximum. Okay. All right. I hate to do this, but I think I'm going to have to go clear my head and see if I can get something. I wish I had some eye drops or something because my eyes are just really bad. But let me run down to my office. Do you mind taking a very quick break? Oh, my head's all clogged up and may be affecting the eyes too. All right. So that was the end of example 5. Now we're moving to example 6. Any questions before we go there? All right. They don't give the function on the figure here, so let's write it down. Example 6. Find the minimum and maximum of the function f of x is equal to sine x plus cosine squared x, okay, on the interval 0 to 2 pi. Okay, closed interval. So when they say minimum and maximum, they're not asking for local, though I think local is important. They're asking for absolute max and min. Okay? So, what would be your first step? Take a derivative. Why do we take the derivative? What's the point? We're looking for the critical values. And you find those by taking a derivative. What do we do with a derivative? 2 things. Second? There's 2 things. First, to observe it and see is there any value where that derivative doesn't exist within that framework. So because your critical points, critical values, are whether either the first derivative doesn't exist or where it is equal to 0. So that's why we take a derivative. We're looking for the critical values, and that's going to be where the first derivative either doesn't exist or is equal to 0. So you tell me what f prime is. Cosine x plus there will be a minus sign, so we'll change that plus to a minus. Okay. And sign will be in there. Anything else? There'll be a 2 in front of it. Yep. Cosine x. Why? Okay. I like to be a little more orderly in it to make sure I don't screw something up. The overall, the big function here, the outer function here is the squaring function. How you do that is 2 times whatever this is to the first power. So that gives you 2 times cosine x. Then I do a chain rule of the innermost function, which is cosine. That's where I get the minus sign. So 2 cosine x times a minus sine x. Put them all together, you get minus 2 sine x cosine x. Yeah. See that? All right. Then what might we do? Okay, yes, we're going, yeah. Okay. The 2 things we do with the derivative, we see if there's any values of x for which doesn't exist within that interval. No, sine and cosine function are smooth continuous functions everywhere. Certainly within 0 and 2 pi. So no, there's no place where the derivative doesn't exist. So that's out of there, okay? The other thing is where the derivative is what? Equal to 0. So I would say first set it equal to 0, and then factor, okay? And what can you factor? Okay, factor out a cosine x, and what does that leave us with? A little louder. A little louder. Okay, yeah, but you got a 1 here. When you factor cosine x out of cosine x, you're left with a 1 minus 2 sine x. You got that part right. Equals 0. What we do now that we've got it factored? Give up and throw it home. No, we're not going to do that. Okay? What do we do? Ever heard of the zero product principle? Sure you have, okay? If you have a product of 2 or more things that equals 0, guess what? One of them's got to be a 0. That's the only way you can get a 0. So let's do it. You do it, use it all the time, okay? Either cosine x is equal to 0, or 1 minus 2 sine x is equal to 0. You do that all the time, don't you, once you factor? Yeah, you do it. So, that first one. What values of x between 0 and 2 pi, if you took the cosine of it, would give you 0? Where is cosine x equal to 0? Pi over 2, that would certainly be 1. So x equal pi halves. Anywhere else? 3 pi over 2. And there are more, but not in that interval. Okay? Every half pi. Negatives, positive, everywhere. All your half pi's cosines equal to 0, but you only got 2 of those between 0 and pi halves. 5 halves pi is beyond it, negative half pi is beyond it that way. So yeah, those 2 values would produce that. So we got 2 potential values. How about the other one? How could you rewrite that? Goodness, my eyes are doing it again. Okay, you could. I prefer to do adding 2 sine x. I don't like negatives so much. Okay, and then I'm going to switch sides and say that 2 sine x is equal to 1. Now what? Divide by 2, and that gives you sine x is equal to 1/2. Now, where is x equal to 1/2 between 0 and 2 pi? Pi over 6 is certainly 1, so x equal pi 6. Any others? Say again? 5 pi over 6. All right? All right, now, hopefully y'all just knew that, but if, say again? Okay. Okay. Well, very good. I'm glad you're doing that. Let's draw the sine function between 0 and 2 pi. Okay? I'm not interested anywhere else, right? Well, there's going to be pi, and here's going to be pi halves, and here's going to be 3 halves pi. Now, how would the sine go between 0 and 2 pi? It goes up to 1 here. So it goes a 1 here, a 0 there, a -1 here, and then a 0 there. And we want pi 6, we want 1/2. Well, it's right there and right there. The 2 I think you were naming are -1/2, aren't they? Right? So we're not interested in that, only those 2. And I think that hits them all, right? Pi 6 and 5 pi over 6. Okay? See that? 4 places where we have critical points, critical values, and then we have the end values as well. So, anyone want to hazard where to start? I like to start at the left and make our way to the right. So let's first do f of 0. And what would that be? What sine of 0? Really? No. Sine of 0 is?
0.
0, okay. plus what's cosine of 0? And 1 squared is 1. All right, f of 0 is 1. Okay, the next one that I see is pi 6. And what is the sine of pi 6? 1/2 plus, and what's the cosine of pi 6?
3 over 2. Over 2. I mean, root 3 over 2.
Root 3 over 2, okay? And then when you square that, what do you get?
3 over 4.
3 over 4, okay? So that would be plus 3/4. And if I add those two together, that would be 2/4 plus 3/4 is 5/4, right? All right. So I got a new high, possibly have our low. Let's keep going. F of, okay, we did pi 6. I think the next one up is pi halves. So let's do pi halves. What is sine of pi halves? What is sine of pi halves? 1, okay? What's cosine of pi halves? 0. 0 squared is 0, so f of pi halves is 1. Next one up, I think, is 5/6 pi. So let's do that one. F of 5 pi over 6. And what's sine of 5 pi over 6? 1/2. What is cosine of 5 pi over 6? Negative 3 over 2, but we're going to square that, and what do we get? Square a negative, you get a positive 3 over 4. So we get another positive 3/4. Seen that before. That adds to 5/4, right? Okay, the next one we hit, I'm pretty sure then would be f of 3/2 pi. All right, what is sine of 3/2 pi? Negative what? 1. Very good. Plus, and what's cosine of 3/2 pi? 0. Okay, so that just is going to be as negative 1. Looks like we may have a new minimum. Okay, and then we'll do f of 2 pi. And what's sine of 2 pi? 0. Cosine of 2 pi? 1. 1 squared is? So we're back to 1 again. All right. What seems to be the case? We have 2 absolute maximum and 1 absolute minimum. 2 absolute, and basically all 3 of those are critical points. Your endpoints are not in the picture anymore, folks. Okay? And on the graph, that's here are 2, I hate to call that absolute maximum. They are, but you just have 2 values of x where that's true. Pi 6 and 5 pi 6. And then one place where it's the minimum value, and that's that. 3/2 pi, it drops way down to negative 1 there. The other values, your 2 endpoints are both at 1, either max or min, and you have one other local minimum here, but it's not an absolute minimum. Okay? But again, I think local minima are important too. Okay. Make sense? Now, this extends to something else. Okay, here's a table for that problem. Okay, they do the critical points first. One happens to be at a 1, one at a negative 1, one at 2 of them at 5/4. The 2 at 5/4 are your absolute maximum. The 1 at negative 1 is your absolute minimum. Your other critical point is a local minimum, I think it is. Yeah, local minimum. But it's not an absolute minimum. Okay? And then the two endpoints, they're both 1s too. So, oh yeah, I was looking for the second one. They did them both in one thing. It's 0 and 2 pi, they're both 1. So. All right, good deal. Any questions on that one? Thought you could forget your trig, huh? No. And by the way, I should say this again, okay? Anytime you're dealing with calculus, you're dealing with trig functions, what mode did you better be thinking? Say again? Radian. Do not think degrees in calculus. Hardly ever, okay, will you want to be dealing with degrees, okay? Now, here comes another theorem. It's an application of our optimization methods that we've just been fiddling with, whether we knew we were calling them optimization methods or not. We prove Rolle's theorem. If f is a differentiable function, now what does that mean? F is a differentiable function. Yeah, you can take a derivative. There are no places where the derivative is not defined. So we're excluding those cusps and things like this where the function, like your absolute value thing, that wouldn't be a differentiable function, okay? So if f is a differentiable function and takes on the same value at two different points, A and B, if it's a differentiable function, that means it's smooth and continuous, okay? Smooth and continuous, okay? Takes on the same value at 2 points, that means somewhere in between those 2 points, you're either going to have an absolute maximum or absolute minimum. Got to. The only exception with that if it was a straight line to begin with, okay? A horizontal line to begin with. And there, everywhere the derivative is 0. So, takes on the same value at 2 different points, A and B, then somewhere in between those 2 points, the derivative is 0. Maybe everywhere it's 0, but somewhere in between there it's 0. Graphically, if the secant between x equal A and x equal B is horizontal, then at least one tangent line between A and B is also horizontal. So that's the illustration of it. If you have at A, you have some value, and at B, you have that same value. Somewhere in between that, if it's a smooth, continuous function, there's got to be someplace first derivative is 0. Okay? So, I probably should have blown this up. Sorry, forgot to. Okay? So that then leads to Rolle's theorem, which is this. Assume that f is continuous on A to B and differentiable on A to B. Now, why didn't they say that altogether? Well, it can be continuous on the closed interval A to B, but differentiable, it can't be differentiable on an endpoint because you don't know what's coming after that. It's differentiable on the open interval A to B. So if f of A is equal to f of B, okay, and it's continuous everywhere, including A and B, but differentiable in between A and B, then there has to exist at least one number C in between A and B, so they say f prime of C is equal to 0. And the thing showed it as a max, it could have been a min. But somewhere in between. You may have several of them in between, but there's at least one C in between A and B where the first derivative is 0. Now, that I think is example 8. Before we get there, let's do example 7. It says, verify Rolle's theorem for f of x is equal to x to the fourth minus x squared on the interval -2 to 2. Okay? Now, what's the first thing we probably ought to do? Second? Okay, that's usually your first best thing to say. We will ultimately take a derivative. I promise you, we will. This is Cal 1. We will take a derivative. Yeah, let's plug in those endpoints to see if indeed f of -2 is the same as f of +2. No guarantee of that, but to do Rolle's theorem, they need to be. So let's do it. Let's do f of -2. What would that be? Second? 16 minus 4 equal 12. Okay. What's alpha of +2? Second? 16 minus 4 equal 12. Okay, so the conditions for Rolle's theorem is true. The f of A is equal to f of B. Got it. Okay? Now we do what? What you've been wanting to do? Second? Take a derivative, f prime of x. What would that be? 4x cubed 2x. And what we're going to do with that? Set equal to 0. And see if maybe there is some place between -2 and 2 where that derivative is equal to 0. What would you do next? Factor. I like that. And what would you factor? 2x. And what do you have left? At 2x squared minus 1. Agreed? Okay? It's equal to 0. Okay? And this, guess what we see right off the top? What do you do with that once you factored it? Yeah, you've already done that. So now we set 2x equal to 0, or, y'all have forgotten your zero product principle? No, you haven't. Of course you haven't. We just did it. Okay? Or 2x squared minus 1 is equal to 0. What does the first one give you? X equals 0, right? Divide both sides by 2. That'll give you x equals 0. There's a place in between -2 and 2 where the first derivative is 0. Is that the only one? Well, let's see. What could you do here? Now that's a little bit of a mess, isn't it? Yeah, let's add 1 to both sides. And that gives us 2x squared is equal to 1. And then divide by 2, and you get x squared is equal to 1/2. And then what would you do? Take a square root, and that gives you x equal to, okay. Usually when you take a square root, you do plus or minus the square root of 1 over 2, square root of 1/2, which would be plus or minus 1 over the square root of 2, which would be, if you wanted to do this, plus or minus 2 root 2 over 2. You don't have to do that last step if you don't want to. This is a perfectly okay form. In the old days, we always rationalized the denominator. Okay? That's not right. It's root 2 over 2, not 2 root 2 over 2. Duh. All right, sorry about that. Talking too fast. Root 2 over 2. Okay? Someone got a calculator? What is root 2 over 2? 1707? about 0.707, right? Which would be between -2 and 2. So we actually have 3 places where the in between -2 and 2 where the first derivative is 0. X equals negative 0.707, x equals 0, x equals positive 0.707. It's actually 3 of them. Actually, more precisely, negative root 2 over 2, 0, and root 2 over 2. Okay. All I, in the interval, -2 to 2, so Rolle's theorem is satisfied with all 3 of those values for C. Okay, now we're ready, I think, for example 8, which is the last example of this section. Okay? Show that f of x, here it is, f of x equal x cubed plus 9x minus 4 has precisely 1 real root. Man, how can we show that precisely? That it has 1 and only 1 real root. Okay? What would be your first step? Take a derivative. I love it. Okay? And what would that be? F prime of x would be 2x squared. Second? Is there more? I mean 3x, I'm sorry. I can't hear and I can't write. Okay. 3x squared plus 9. Very good. All right. Now, guess what that means? For any value x you put in there, guess what that number is? Say again?
Positive.
Positive, right. You put a negative number in for x, square, it becomes positive. 3 times a positive number is going to be positive. Put a 0 in for x, 0 plus 9 is positive. Put a positive number in for x, square it is positive. 3 times a positive number is positive. That's always positive. Always, always positive. What does that mean? The function's always increasing. Always increasing. Okay? Now, if it's always increasing, that means it never doubles back on itself, right? Now all you have to show is there is at least 1 real root. And how you do that is just pick a value for x. It's the easiest value for x. Easier. 0. Plug in a 0 here. Alpha 0 would be -4. Now use the next easiest one. 1. And what would alpha of 1 be? 6. So we have alpha of 0 is a negative value. Alpha of 1 is a positive value. It's strictly increasing in between. There had to be one place that because it's a nice, smooth, continuous polynomial function, it has to cross the x-axis at one. It has to cross the x-axis, and because it's strictly increasing, it can only cross it once. So sure enough, that shows you only have 1 real root. First derivatives are really useful, aren't they? The answer is yes. Okay. All right. There is a little historical perspective on Pierre de Fermat, who we had his, what do we call it, theorem? Yeah, Fermat's theorem. It says sometime in the 1630s, the decade before Isaac Newton was born, the French mathematician Pierre de Fermat invented a general method for finding extreme values. Guess what? If it was before Newton was born, no one knew how to do a first derivative yet. But he found the general method for doing it. Okay? So, in this one little blurb here, I see Newton mentioned, I see Fermat mentioned, I see Leibniz mentioned, I see René Descartes. Around the same time, they were, if you look at their dates there, Fermat was born 7 years after Descartes, and then he lived another 15 years longer, so he was older. And this is Jasmine's here. Has anyone else come in since I called roll? I don't recall anyone. So, around the same time, René Descartes developed a different but less effective approach to finding tangent lines. Descartes, after whom Cartesian coordinates are named, was a profound thinker, a leading philosopher and scientist of his time. He regarded today as the father of modern philosophy and founder, along with Fermat, of the analytic geometry. But a dispute developed when Descartes learned through an intermediary that Fermat had criticized his work on optics, being very sensitive. Then Descartes retaliated by attacking Fermat's method of finding tangents. Only after some third-party refereeing did he admit that Fermat was correct. Okay. However, in subsequent private correspondence, Descartes was less generous. So guess what? We had great, fabulous mathematicians and philosophers who could still be pretty petty and hold grudges. They're just human, okay? But they didn't mind their own mental form too well. There's a bunch of potential paper topics there, okay? Who was Fermat, who was Descartes, who was Newton, who was Leibniz, okay? Now, some of those may have been taken. How did Descartes establish the Cartesian coordinate system? There's one. What were both Fermat's and Descartes' methods for finding tangent lines and, taking, in a sense, derivatives, though they couldn't do it. They hadn't been invented yet. The dispute that rose between the two, or the criticism they made of each other, and there's a bunch of different paper topics there, so I'll let you decide. But, hint, this little blurb here cannot be a source for your paper. You have to get your source from outside the book. This is inside the book. You can't use it. It gives you ideas, but find your sources elsewhere. All right, you want to do the preliminary exercises? Preliminary questions? Yay or nay? Up to you. What you think? No, I heard no's. Homework exercises then. Do number 1. It has at least 5 parts there. Then do any of the odds 3 through 19. There's a whole passel of them there. I would do more than one. Do a couple of every type, or 1 or 2 of every type. Then do any of the odds 21 through 27. Now, they say 25 needs a graphing utility, and 27 seems to indicate you need a computer algebra system. See if you can do it without it. If you can, fine. If you can't, don't sweat it, because unless you happen to have a graphing utility to do it. Okay? Then do any of the odds 29 through 57. There's another huge pile of them there, and again, do probably definitely more than one. Several types of the problems. Okay, then do 59. Again, it's a subpart problem. Okay, and some of those may require a graphing utility. My eyes are doing it again. Then do either 61 or 63 or both, either 65 or 67 or both. And then there's some with proofs. You can do these if you want to. I'm not going to require these, but any of the odds, 69 to 81. Okay? And then then do 83. That's the only one like that. Now it says you need a graphing utility, so if you can't do it without one, you can, and don't have one, you can skip that if you want to. Then do any of the odds 85 through 89. Okay. Further insights and challenges, I usually look at those just to see if there's a potential paper topic somewhere lurking in there. I don't particularly see any. However, if you go back a little bit, you can see that they have modeled antibiotic levels in your bloodstream that if you want to follow up on that and perhaps find a paper topic that would deal with that, you could. 78 deals with the Bohr radius of a hydrogen atom. So if you're interested in that kind of thing, that would be okay too. So a little more physics and calculus, but you've got to have calculus to do it. There's also in question 79 some questions on resonant frequencies, and that's a pretty interesting topic itself as well. Okay, so I'll let you look and see if there's anything else you want to do. Any questions? 4.2. Okay. So eyes are doing it again. Yesterday they were sort of like twitching or I don't know what to call it. They were really light sensitive, and I was afraid it might be. I've only had maybe 2 in my lifetime migraines, but that's exactly how they started. It seemed like light was flashing, and I got a little headache, but it never progressed past that. Well, the itching and doing that, but they're not as flashy as they were yesterday, so hopefully whatever it is, it's going to pass. I only got 4 classes of teaching today, so for some reason this is having trouble pulling it up. Yeah, there it goes. Moving to 4.3. All right, slideshow 4.3. Seems like most of my experience in various texts, they would follow very soon after Rolle's theorem, usually in the same section, the intermediate value theorem. Okay? But this one, the way they split it up, they do it in the very next section. I think it makes more sense to talk about them together. Okay? But remember, Rolle's theorem required the f of A equal f of B, and then if that was the case, you said you had at least one place where if it's a smooth continuous differentiable function, and f of A was equal to f of B, then there had to be a C in between where the derivative was 0. Okay? Part of the argument was, since the secant line is horizontal there, then there has to be a horizontal tangent in between. Well, now, sort of doing the same thing, but you don't have as much of a restriction here. If you have any two values, okay, again, smooth continuous differentiable function. Got to have that on the interval A to B, closed interval A to B. And f of A doesn't have to equal f of B. But if you do the slope, f of b minus f of a over b minus a, that's delta y over delta x, the slope of that secant line is going to equal the slope of at least one tangent line in between A and B. There is a point C that has the same slope of the tangent line as that secant line. By the mean value theorem, there exists at least one tangent line parallel to the secant line. And it basically follows almost the same reasoning, and certainly the graphical explanation would be pretty much identical. Okay? One way to think of it, well, let's see. Here is the mean value theorem written out. Oh, my eyes. All right. Assume that f of x is continuous on the closed interval a to b and differentiable on the open interval a to b, just like we did Rolle's theorem. Then there exists at least one value c in the interval a to b, such that f prime of c is exactly equal to the difference of the slope between those 2 points. Delta y over delta x, f of b minus f of a over b minus a. There has to be some place on that, some value c in between those two, where the derivative is exactly equal to the slope of that secant line. Okay? Intermediate value theorem. Okay. There's some intermediate value between those two extreme values where the derivatives are the same. Derivative is the same as the slope. All right, here's sort of a graphical way of approaching a proof, you might say. Okay. If that's your original secant line, then move parallel up toward that maximum, keeping it parallel secant lines, and then at some point you're going to have a parallel tangent line. Okay? So that's just sort of a graphical representation, but it sure lends, to me, visual support that that intermediate value theorem is true. Okay, and that's your graphical insight there. There's also a conceptual insight here that if you have this as your mean value theorem, you can then say, well, let's just multiply both sides of the equation by that denominator. So we have f prime of c times b minus a is equal to f of b minus f of a, and that basically looks like a lot like your point slope formula. There's the slope, and here's your points, ab, f of a, f of b, you know. So it's just basically saying almost the same thing. And that can lead to how you do your slope of a tangent line as well. Okay? All right, the conclusion here. The mean value theorem turns this approximation into an equality by replacing f prime of a with f prime of c for a suitable choice of c on a to b. Okay. All right. Let's move on to example 1. No. There's the what we just, oh yeah, I went backwards. All right, there was the, where are my eyes? Okay, there was your rearrangement, flip sides as well. Alpha B minus alpha A is equal to F prime times B minus A. Okay. This could be Y2 minus Y1 is equal to F prime times H2 minus H1. Okay. Now, don't know what special significance of that is, but there it is. All right. Now here is example 1, I think. Hope the eyes hold out for 20 more minutes. Okay. It says verify the mean value theorem with alpha of x equals square root of x. Okay, I have to get my pen color back. For this function, where a is equal to 1 and b is equal to 9. Okay. Such a hard time focusing, which again makes me feel like almost like the migraine type thing. Says verify this. Okay, so let's do it. What would be the elements of your mean value theorem? What are the requirements there? Well, we need to determine what alpha of 1 is and what alpha of 9 is. That's pretty easy to do, right? Here's your alpha of x. So what's alpha of 1? The lower point, the A. What would that be? Square root of 1? 1. All right, not that hard, folks. Alpha of 3. I'm sorry, alpha of 9. Jumping ahead. Square root of 9? 3. Okay. Well, I answered it for you, but okay. Now, mean value theorem says that part of this is glare. Looking at this really bright screen, I think that's really giving my eyes fit. Here's your function. What's required for the function? It has to be smooth and continuous from A to B, including 1 and 9, and differentiable between 1 and 9. It doesn't have to be differentiable at 1 or 9. This one happens to be. That you can continue taking derivatives past that. You could not have included 0, because this is not differentiable at 0. You could have said from 0 to 9, that would have been fine, it would have been continuous here, but not differential, but it would still have been differentiable from open interval 0. Anything past 0, you can take the derivative. You just can't take it at 0. Okay? So anyway, we've got the points here. Now, what did the mean value theorem say? The slope of the secant line connecting those 2 points. Well, what is the slope of that secant line? You can do that, can't you? What's your slope formula? Goes way back to Math 100 probably. High school, somewhere. What's your slope formula? A little louder? I can't hear. Okay. Rise over run. Yeah, mx plus b is your slope-intercept form. But yeah, rise over run, which would be, okay, y2 minus y1 over x2 minus x1. And what would be your y2 here? I'm sorry? You could do that. I usually do it the other way, but you could do 1. What's your y2? Say again? No, that's a 9. The square root of 9 is 3. What's your y2? Three, yes, 3. Over. Second? Okay, you're saying 9 minus 1, is that what you said? Well, if she chose the y2 to be 1 and the y1 to be 3, then you have to stick with that and call x2 1 and x1 9. Now, I don't usually do it that way, but you can, because guess what this gives you? Negative 2 over negative 8, which would be 1 over 4. Guess what? If you'd have done it the other way, starting with this being your y2, then you have 3 minus 1 over 9 minus 1. You get the same answer, 2 over 8, which is still 1/4. Okay? So there is your slope. Okay? Now, what does the mean value theorem tell you or suggest to you? There is some point on that curve that has the same derivative slope, okay, as that, as your slope of the secant line. So now we would do what? First thing I would do is rewrite that. How would you think I would want to rewrite that function? How can you rewrite that function? Alpha of x equals square root of x. Hint, I'm trying to take its derivative. A radical is easy to take derivatives of. X to the 1/2 power. All right. And then do what? Take a derivative. F prime of x would then be 1/2 x to the minus 3s. I can't see. Come on, my eyes are crazy. Okay. No. Negative 1/2. No wonder I couldn't see. I was writing the wrong thing down. I was doing an integration and a derivative. Negative 1/2. It's 1/2 x to the, subtract 1 from 1/2, you get negative 1/2. Now let's rewrite that, perhaps back in radical notation. What would that be? What would that be? What would that be? Well, your only numerator here is a 1. In the denominator you have a 2, and then if you drop this down and put it in the denominator, you lose the not negative sign on the exponent, and it would be x to the 1/2, so it would be 2 root x. I say root x and write root 2. There's something wrong with my head today. Okay. And, yeah, okay, that's it. Now, that is your f prime written back in radical notation. Well, what do we say this had to be? Intermediate value theorem. Same as the slope of the secant line. Slope of the secant line we found was 1/4. So we set this not equal to 0, but equal to 1/4. That's what we're trying to show. So what could you do here to solve for x? Help me, help me. How do you solve a proportion? Second? You could guess some values and plug in, sure. What would you guess? Second? Okay, square root of 4 would be, you know, you're right. Goodness gracious. I was already doing the math in my head, and that is a 1/4. It's not a 1/2. Sorry about that. Okay. Now, what were you saying? If you plug in a 4 for x, square root of 4 is 2, and then 1 over 2 times 2 is 4. So you're absolutely right. X equal 4 would work. Okay? Now, I don't know if you saw that from the graph. Oh, of course not. You wouldn't have done that, would you? No. Okay. But what I was getting at, in general, if it wasn't one that's so obvious as this one, what you can do if you have a proportion here, one ratio equal to another ratio. Have you ever heard of cross multiplying? That's what you do here. That would give you 2 root x is equal to, that's 2 root x times 1 is 2 root x is equal to 4 times 1 equal 4. Divide both sides by 2, and that gives you the square root of x is equal to 2. Then square both sides, and you get x is equal to 4. Okay? Now, you have to be careful when you go around squaring both sides to make sure you don't get an thing that's undefined, but that gives you something exactly like you would want, x equal 4. So either by observation, as one did, or analytically the way I showed it here, there is that value that where x equal 4, the slope of the tangent line is the same as the slope of that secant line, 1 over 4. So sure enough, that works. Now again, that doesn't look like a 1/4 slope to me, and the reason is there's one on the horizontal scale, there's one on the vertical scale. They're not equal, so that looks a bit too steep for a slope of 1/4, but that's because they expanded the y scale and shrunk the x scale. Okay. Yeah. Okay. Now, the mean value theorem has a corollary, meaning extend it just a little bit, and you can come up with sometimes all sorts of really interesting applications or variations on that thing. And here's your corollary. If f of x is differentiable, now what will that mean? For a function to be differentiable? It has a derivative. And for it to have a derivative, it means it has to be continuous. You can't have a derivative if you have discontinuous function. So it means continuous, but it also means smooth. Remember, a cusp doesn't have a derivative. The derivatives are not the same at that point. So it has to be not just continuous, but also smooth. So if f is differentiable, meaning it does have this, and that derivative is 0 for all x's on the interval from a to b, then f of x has to be a constant function. If that derivative is always 0, that means that's a constant function. If it's always 0. In other words, f of x equals c for some constant c everywhere in that interval from a to b. Okay? That's a pretty, it's something we talked about a long time ago, so why bring it up again? But this is just saying the mean value theorem basically proves that's got to be the case. Or you can use it to prove that. Okay. Let's get this one more theorem in. I think we'll be fine. This sort of builds on one that we had a little bit earlier. Okay, an example. The sign of a derivative. Okay, we've been talking about when the derivatives are 0. That means you have a horizontal tangent line. Okay, what if your derivative, let f be a differentiable function, meaning smoothly continuous, also open interval a to b. If this derivative is positive for x, every x on a to b, that means that f of x is a strictly increasing function. It never decreases. It never even flattens out completely to 0. It's always increasing. We have a name for that. It's called monotonic. Monotonically increasing. Always increasing. Never decreasing and never even repeating itself. But on the other hand, if f prime is less than 0, in other words, a negative derivative for all x's on that interval a to b, then that is a decreasing function, okay, on that interval a to b. Okay? That means the slope is always downhill. Never horizontal, never positive, always negative. That's what your first derivative tells you. All right. There is a little proof here, and I think we're out of time, but these are just illustrations of what we just said. And basically it goes the other way too. If you ever have a function that is strictly increasing, then you know its first derivative is always positive. The tangent line always have a positive slope. If it's everywhere decreasing, that means the tangent lines have a negative slope. So that's sort of a graphical reversal of that. Now, is this? Yes, that's going to be example 2. That's what we'll pick up next time. All right, let me give you a few homework exercises in this section. Okay, we'll begin with example 2, top of the page. All right, homework exercises here. We made decent progress in this section today. Do any of the odds 1 through 7. I think you can do it either 9 or 11 or both if you choose. I think you can probably do 13, though it says you need a graphical interface. And we'll stop there, and because we'll pick up the rest of those next time. Good deal. Okay, folks, remember, we only have 3 more classes. Monday and Wednesday of next week, and Monday of the last week. Okay? That's all, folks. Now, what that means for me is See, we've lost 4 classes out of our 20 this summer, okay? So we've lost a quarter of our classes. Going to have to do a little bit of moving on and maybe skipping a little bit or moving quite fast to get the rest of chapter 4 done before our time is over. But the very last thing in chapter 4 is called antiderivatives. And so we'll have to skip a few sections to get there. I thought it was somewhere in here. I don't see it. I thought antiderivatives showed up in chapter 4. Maybe they pick up in 5. Flight optimization. I know we've got to skip that one. That's just a little too long. Nope. Okay. So, we will get started in chapter 5. I do want to at least touch the main topics in 5. The integral, okay, and I'm going to try to hit at least a little bit on the integral. It's going to be tough, so we're going to have to sort of fly next week, and probably Monday of the last week touch a little bit on chapter 5. That's going to be then your last test will be your final exam. It'll be what we do in chapter 4 and maybe a section or 2 in chapter 5. Okay? We'll skip some of the upper sections here. We just can't do it. But some of these are really important. We've got to at least touch them. So that's how we'll go from there. Any questions? Sorry we lost so much